Hi everybody, my name is Hyojong Shin, working for KT. KT is an internet service provider in Korea. My topic is a DNS anomaly detection and analysis system. We've developed this system that monitor KT's DNS server farm and find out the problem of DNS. Firstly, I'll introduce CoreNet DNS system. CoreNet is the name of KT's commercial internet service. CoreNet has more than 20 cache DNS server farms. Each server farm advertises the same IP address using any-case routing. Each DNS server farm serves its local POP. CoreNet has a star topology. There is a central DNS server farm in the center of the star topology. A central DNS server farm takes and serves queries for another server farm when the server farm fails. A DNS server farm consists of IPS, layer 4 switch, and multiple DNS servers. Each DNS server farm advertised 2/32 IP addresses. One is primary DNS IP address, and the other is secondary DNS IP address. As I said in my previous slide, we have many DNS server farms, and actually we have more than 150 DNS servers. Problem or accident of DNS happen simultaneously from many server farms. It was difficult to figure out what problem happened on DNS. Before this system was installed, we had to dump DNS packets on each DNS server and analyze the problem. It takes so much time, and it's not easy to find out the problem instantly. After this system is installed, we can easily investigate which server farm has a problem and what the problem is. Our system consists of one central detection system and multiple local analysis systems. A local analysis system has been installed per DNS server farm basis. A local analysis system attached to a DNS server farm through two tabs. These two tabs are located in between IPS and layer 4 switch. Due to a tapping location, we can analyze DNS packet throughout the servers of the farm, not server by server basis. Currently, we installed two local analysis systems. There is one local analysis system in central DNS server farm. A local analysis system captures all port 53 packets to and from DNS server farms and inspects their contents with predefined rules, and sends analytical results to the central detection system. The central detection system gathers the analytical results from all local analysis systems and then detects DNS anomalies. This slide shows the system's user interface. Actually, all Korean characters of this user interface has been replaced their corresponding English representations. Main menu consists of real-time analysis, past analysis, offline analysis, local system control, and threshold for anomaly detection. Real-time analysis and past analysis have the exactly same sub-menu. These sub-menus are DNS traffic, tab and data, and anomaly detection. Real-time analysis shows analytical data of a present point of time. We can retrieve all the analytical data from past analysis menu. Each DNS traffic submenu shows either count or ratio values on packet analysis. Each tab and data submenu shows a ranking of frequently used domain or source IP addresses. This slide shows the number of captured packets on April 9 to 10 with 1 minute sampling rate. I'll explain this submenu one by one. This slide shows queries and answers submenu of DNS traffic. This graph shows the number of total packets, client queries, answered for client queries, recursive queries, and answered for recursive queries. This graph shows many curves at the same time, but user interface provides an option to select individual curves. This slide shows response ratio submenu of DNS traffic. We calculate response ratio with the number of answer packets divided by number of query packets. Red curve shows the response ratio of recursive queries. Blue curve shows the response ratio of client queries. You can see response ratios vary from local system to local system. In a normal case, red curve is slightly lower than blue curve. This slide shows the response ratio of primary and secondary DNS IP address. We'll calculate response ratio of primary DNS IP address and secondary DNS IP address separately. Red curve shows the response ratio of queries that come through primary IP address. Blue curve shows the response ratio of queries which come through secondary DNS IP address. This slide shows the cache hit ratio submenu. This slide shows concurrent users submenu. Red curve shows the number of source IPs per minute. Blue curve shows the number of queries per source IP. This slide shows TCP sessions submenu of DNS traffic. We classify the TCP sessions as 4 types: only query, time over, empty, and normal. Only query session have TCP start, DNS query, and TCP finish. Time over session doesn't have any TCP finish process. Empty session has TCP start and TCP finish process without any DNS queries. This slide shows query types of many of DNS traffic. These 2 graphs shows the distribution of query types: type A, MX, PTR, etc. You can see there are abnormal users in local system 1 who generate huge amount of PTR queries. In a normal case, the ratio of type A query is very high. This slide shows answer types submenu of DNS traffic. These two graphs show the distribution of answer types. Type no error, subfail, name error, etc. The type no error answers in local system 1 were incurred by users who generate PTR queries. This slide shows anomaly queries submenu. We regard queries which violate the format constraints of DNS header as anomaly queries. These queries have been generated by malicious users. From now on, I'll explain tab and data submenu. This is source IP submenu. The category field will be changed by clicking combo box. The category tab and source IPs are ranking of source IPs who generate queries. Tab and source IPs with type A is a ranking of source IPs which generate type A query. The last column of this table shows ranking variation. Newly ranked source IP address may be regarded as suspicious users. This slide shows query name plus source IP. The category tab and query name plus source IP is a ranking of combination query name and source IPs. If one source IP generates the same query continuously, it will be ranked very highly. Tab and query name plus source IP to type A is a combination of query to type A and source IP. Tab and black domain plus source IP is a ranking of combination of black domain to combination of queries to black domain and source IPs. These black domains are defined by Korean Information Security Agency. Currently, the number of black domains are 5,000. This slide shows query name submenu of tab and data. The category tab and query queue name is ranking of query name. Tab and query name with type A is a ranking of query name with query type A only. We also count queries to authoritative DNS servers, which serve recursive queries. For root server, JRoot server is frequently used because the mirror site of JRoot is directly connected to Cornet. We make a ranking for top-level domain. We also make a ranking for second-level domain and third-level .kr domain mixedly. Many Korean websites have domain names with second-level.com, .net or third-level.kr. With this top and second-level domain, third-level domain ranking, we can easily find out which sites are popular for Cornet users. I'll explain anomaly detection logic briefly. Anomaly detection is based on the variation ratio of DNS traffic. Basic ideas on detection formula are following. Use the collected parameters of DNS traffic. Keep the limited history of values on each parameter and put more weight on recent data. And then we make a decision for anomaly with those threshold values. When anomaly detected, we check the details on who or what incurred problems with tab and data pages. These are indicators of anomaly: increase in number of DNS packets, increase in number of queries to DNS server farms, secondary IP addresses, decrease in cache hit ratio, etc. This slide shows an example of anomaly detection. This table has 8 time period and 9 indicators. We use 4 warning levels like green, yellow, orange, and red. Second row shows threshold value for this warning level. Red means the situation is very critical. I'll explain 2 cases of utilizing the system. The first one is to detect unexpected increase on MX queries in February 2007. At that time, the traffic was doubled and response ratio was just 10% or higher. It means most of client queries are dropped. We investigate what queries they are, who generate, what query types they are. We can analysis result that multiple source IP addresses from many server farms kept generating MX queries. It was a kind of mailworm situation. We blocked the traffic from the corner to the infecting system. Actually, it's in USA. The second case is to detect tons of queries on time.list.gov in March 2007. The amount of queries had been doubled or tripled at all DNS server farms. We investigated what queries they are and who generates. More than 60% of queries on time.list.gov. Those source IP address from some home gateways. At that time, the NTP server of list.gov was changed its name from time.list.gov to the other thing. But Korean home gateways still use their name as NTP servers, and that makes these queries. And we advised the company to patch their firmware. The plan of this year is to install another local systems to cover all DNS server farms of CoreNet. And we will improve the anomaly detection logic. That's it. Are there any questions?
So, Mark Oster's VeriSign. I really like this presentation. Actually, this is one of the first presentations I saw where cache utilization hit rates was actually presented. And I think that is, we've had multiple presentations over time from FRoot and JRoot and so on in terms of the root servers. I think it'd be very interesting to see some more sort of behavioral sort of characteristics that are coming from caching name servers like what you have put together. And I would like to see that in the future.
Okay.
Hi, Isaac Salpeter from Amazon. Have you been doing any anomaly detection in the time domain, or has it been primarily based on query type and response types, or are you actually doing time domain analysis on response times?
Actually, real-time analysis cannot catch the time domain parameter like response time, and we have a main menu offline analysis. With the offline analysis, we can gathering the information for response time also, but it's not easy to gather time information from real-time analysis.
Okay, and Sorry, one other question about that was why did you take the approach of deploying a server based on taps or a collector picking up off of a tap as opposed to a local agent on the name server?
Because we have so many DNS servers, there is no tab can install between layer 4 switch and DNS servers. That's the reason.
Thank you.
Okay. Thank you very much.